Hi there, my name is Charles Sipa. Welcome to another presentation on differentiation. This time we are focusing on differentiation of logarithmic function base e, and we're going to take advantage of that. We now know how to differentiate the exponential function base e, and from that we're going to get a lot of derivative in a very easy way. Actually, what we're going to do now, we're not going to use the first principles. We're going to use the properties of log function and exponential function you should know to arrive at derivatives of exponential functions and logarithmic functions arbitrary base a. So let's start this way. We saw in the previous presentation, we presented the derivative of the function y is equal to e of x. I think you remember that the derivative here, dy dx, was exactly e to the power of x, but we took it to the general situation whereby the argument was not a simple argument like this, like when we have y is equals to e to the power x squared, and we agreed that the derivative y prime is going to exponential function is going to bounce back as it is, returning the same argument multiplied by derivative argument, which in this case is going to be 2x, and then multiplied by 1. And that time I told you that I was reminded you that 1 was actually equals to log base e of e, which is actually lim of e. So now I would like to write this exactly in full as e to the power of x multiplied by 2x multiplied by lim e, in this case replacing 1. You will see why this is important later. I'll leave it there for now. Now coming to the derivative of lim base e, logarithmic function base e, what you can do is, we know that the log function is the inverse of e. We said that before. So this is, we can apply the inverse function on both sides here and say e to the power y equals to e to the power lim x. And from properties of inverse, we know that this takes us to x. So now, from what we've seen here, that the derivative of the exponential function is the exponential function itself multiplied by the derivative of the argument. So we are going to apply differentiation on both sides here. I'll just use d as a differential operator, and d of x. So what you're going to get here, you're going to get e bouncing back multiplied by the derivative of y with respect to x. Remember, y is our function lim x. Equals to, here I'm going to write this explicitly as derivative of x with respect to x. Normally we would write 1, but for now I'm leaving it like this for a purpose again to make you understand what I would like you to understand. So now check. Here we're targeting the derivative of y. We've got a placeholder here for derivative of y, so we can make derivative of y here substitute formula by dividing both sides by e to the power 1. So then what we have, we are going to have dy dx equals to dx divided by e to the power 1. But we've seen here that e to the power y is x, so we can rewrite that as 1 over x, and note that x is the argument of our lim function. 1 over x multiplied by the derivative of x. That way I can say we have arrived at the derivative of lim x. Now let's read this carefully and see what, and listen to what it says. The derivative of lim x is equal to 1 over its argument multiplied by the derivative of the argument. I think you can see here again that this question of multiplying by derivative argument is coming out natural like that. This is actually what we call chain rule. We've been using it without giving it a name. but now I think we're familiar with it. We've done it several times. We can now name it chain rule, and you will see it in your text. It's named chain rule. So simple derivative of linear function natural base is 1 over its argument multiplied by the derivative of the argument. So then let's look at an example. Here's an example. We've got ln x squared plus 2x is to tend to be like a kind of chorus if we go back to what we've seen here. What is said here is just said ln x derivative 1 over the argument multiplied by derivative of argument. I'm avoiding to say 1 over x because as you can see here, the argument of ln is not just x, it's another plus 2x. So I'm going to say 1 over the argument x squared plus 2x multiplied by the derivative, of course, with respect to x of the argument x squared plus 2x. I'm writing so explicit now because it's the first example, but as you get experience, you can do some shortcuts. Here is going to be 1 over x squared plus 2x multiplied by the derivative here is 2x plus 2, which is going to be equals to 2x plus 2 over x squared plus 2x. One thing very interesting, which is going to be important later, is that note that the derivative of a linear function is always a rational expression. That is very important. Let's come here now to the second example. We've got y is equal to ln of sine 2x. So we say dy dx. You can see I'm using different notations here so you can get used to them. Dy dx is going to be 1 over the argument, which is sine 2x multiplied by the derivative of the argument, which is cosine 2x. But note that the argument here is also a function, so when we differentiate it, we invoke its immediate derivative, which is cos, and then multiply by the derivative of the argument. That's how the chain rule works. Then, simplifying this, we have got 2 cosine 2x over sine 2x. As you can see again, you have got a rational expression, but this one you can simplify it to 2 cot 2x. So there is an example for differentiating logarithm base, natural base logarithm function. So let's turn to the differentiation of a general exponential function base a. Again here, I'm not going to use the first principles. I'm just going to use what we already know and exploit it to see whether we can get a derivative in an easier way here. So here what we're going to do, we now know the derivative of the linear function natural base. So what we're going to do here, we're going to apply ln on both sides here, which is going to be ln of y equals to ln of a to the power x. Simplifying here, we've got x ln of a. Now notice that ln of a is a constant, so when we differentiate here, it's like we're differentiating 2x. So now if we differentiate this side, according to what we've seen, we said this is going to be 1 over the argument multiplied by the derivative of the argument. Why am I saying dy dx? Because I know that this y is standing for this y, and it is a function of x. So dy dx, and that's actually the derivative we're looking for, equals to derivative of x. I'll write it as exactly derivative of x with respect to x, because x is the argument of my function there, multiplied by ln a. Now, we would like to make dy dx subject to formula. So we multiply both sides by y, get dy dx equals to, or multiply on the left here, y multiplied by dy dx multiplied by ln of the base. But notice that y here is actually the exponential function there. Then we write this as a to the power of x multiplied by dx multiplied by ln of the base. Now I think you're going to understand why I was writing this way, taking that one, calling ln of the base, which is the base of the function there. Now what we've arrived at here is that the derivative of exponential function, we've arrived at the fact that the derivative of exponential function y equals to a to the power of x is a to the power of x. In other words, the exponential function always bounces back in the derivative, multiplied by the derivative of the argument, multiplied by the ln of the base, like we've seen there. So then, now looking at examples for this type of exercise, we've got y is equal to 20 to the power x to the power 4. So now, I'm no longer going to apply ln on both sides. I'm going to use what I know. We know that this exponential function is going to bounce back in its derivative as 20 to the power x to the power 4 multiplied by the derivative of argument, in this case, which is going to be 4x to the power 3, applying the power rule, multiplied by the ln of the base, which in this case is 20. Then what is left here is for us to simplify and write this nicely as 4x cubed multiplied by 20 x to the power 4 multiplied by ln of the base, which is 20, and that's our derivative. I think it's very easy to remember that if you are differentiating an exponential function, it always bounces back exactly as it is. It comes to be complete derivative when it's multiplied by the derivative of its argument and multiplied by the logarithm of the base. Now, coming this side, dy dx, we're going to say 5 cosine x squared multiplied by the derivative of the argument here, which is going to be minus sine x squared, and cosine is a function, its immediate derivative is sine, but it's got an argument x squared multiplied by 2x multiplied by ln of 5. So what is left there, you can simplify and write that derivative nicely. So let's move on to the next type of derivative. Now what we're going to do, we need to know how to differentiate logarithm function general base a. So we know from properties of logarithm function that we can always change the base. So if we want to change this base, in this case, we're going to change it to what we already know what to differentiate, which is logarithm natural base. So this is going to be ln of x divided by ln of a. Maybe you might have forgotten the formula for changing base, but it works out exactly this way. So then now, when you're having this, you are having here 1 over ln a, which is a constant, multiplied by your ln function. Now the derivative is going to come out very easily as dy dx. Remember, ln function derivative is 1 over the argument multiplied by the derivative argument. Now the argument here is x. We know that this is dx, which is equals to 1. And normally we don't write it. I was writing it explicitly so that I can put my argument as clear as possible. So now that we know what happens, we're just going to have 1 over ln A multiplied by 1 over the argument that multiplied by 1, which is that, which normally we're not going to write. Then simplifying, we've got here the derivative of log base A being 1 over ln A multiplied by x. We're done there. So now our last examples will be the following. What did you see? We saw that the derivative here of this is now going to be 1 over ln of the base multiplied by 1 over the argument, which is x squared, plus 2x multiplied by the derivative argument, which is going to be 2x plus 2. Now simplifying, we're going to have this as 2x plus 2 all over ln A in brackets x squared plus 2x. That will be the derivative of a logarithmic function. Now I'm going to leave this one to do it yourself, and I hope you are going to win with this one. Otherwise, at this moment, I hope you noted the highlights, which are that when you are differentiating the exponential function always bounces back in the derivative. And in the general case, it also happens exactly in the same way when you are differentiating exponential function. That same exponential function will appear in the derivative multiplied by the derivative argument multiplied by the ln of the base. Then the rest, what you can do now is to part from here, doing this exercise, and then get your text and do similar exercises and get familiar with this kind of differentiation. Others, for now, I would like to say thank you for listening.